Hi folks, welcome back. I hope you're all doing well. Today I want to make a continuation of my last video, and in my last video I had taken a high-level look at the design of the WebAssembly instruction set. And today I want to take a look at this paper which constructs an automated proof of the soundness of the WebAssembly instruction set. This was done by Conrad, who's a PhD student at the University of Cambridge and whose research has been around formalizing WebAssembly. So if you don't know what WebAssembly is, what the instruction set looks like, I'd encourage you to go look at my last video to get some background. What the author has done in this paper is to encode the semantics of the WebAssembly instruction set into Isabelle, which is an interactive theorem prover embedded into ML, the ML programming language. And using this formalization of the semantics of WebAssembly, they have proved type soundness properties of this instruction set. And very notably, while doing this proof, they actually found a few bugs in the original specification. And this led to the specification being tightened up in those few corner cases. Basically, what this meant was, without those fixes, the type system in the original spec would have been unsound. And that's the major motivation for why you'd want to do something like this in the first place. If you look at the instruction set, it's fairly straightforward, fairly simple to understand, and you might wonder what you get out of going through this very detailed effort to formalize the whole thing. And what you get is this certainty, the certainty of having a formal specification that can be automatically verified by a system, and the certainty that as you've done this, you've accounted for the entire range of semantics of this instruction set. As I go over this paper today, my goal is to give you a high-level flavor of how these kinds of formalizations and proofs are structured rather than go into all the nitty-gritty details of the proof. I'd encourage you to go read the paper yourself if you're curious. You can also go to Conrad Watt's homepage where he has a downloadable archive of all the Isabelle code that formalizes WebAssembly. The very first thing you have to do when formalizing this instruction set is to come up with an abstract representation of it. This is akin to an abstract syntax tree when you're parsing and compiling a language. So for example, the types available in WebAssembly are pretty limited. You basically just have 4 types: int 32, int 64, float 32, and float 64. Once you have those types, you can then start encoding all the instructions. You have control flow instructions like loops and ifs. You have blocks of instructions. You can call other functions. You can load and store local variables. You can grow memory. You can access memory. You have unary and binary operators that operate on values on the stack. And here you see the enumeration of the binary operators. So for example, add, subtraction, multiplication, etc. are binary operators that expect 2 values on the top of the stack of the appropriate type, perform the operation, and then push back the result. So what you've done here is simply created an abstract representation of the instruction set. Once you have that, the next step is to define what you call the small step semantics of the language. And the idea of small step semantics is to define individual tightly scoped steps that take one expression in the language to another expression that is slightly simplified. And if you've specified small step semantics for all the operations in your language, you can keep applying them one by one, making these tiny transformations until you arrive at the final result of the computation that is expressed in those instructions. Let's take a very simple example. What's happening in these instructions is that you push a few numbers on the stack. You push 4 and then 2 and then 1, and then you add them. In the very first small step, we take these 3 instructions and reduce them. So that means we take 1 and 2, we pop them off the stack, and we replace it with the addition of those 2 numbers, which is 3, which means this set of instructions on the left here reduces now to this set of instructions over here. And you'll notice that the 2 and 1 have been replaced by 3 over here, and one of the add instructions has gone away because it has been executed. And you do the exact same thing one more time, and then you're left simply with the constant 7 on top of the stack. As part of your formalization, you'd have to specify the small step semantics of every single instruction in WebAssembly. When you're defining these semantics, you have to model the state of the program that you're running. And this is what the author calls a configuration. And the configuration encodes all the state that you're operating on. And then in your small step semantics, you define how configurations change at every small step. In the case of WebAssembly, each configuration consists of a stack of all the abstract operations, a program store, which is your memory, and a list of local variables. We also have what they call an instance index, which indicates what part of the store are owned by the currently running program. And what this models is local functions scopes. Now, this modeling is fairly simple for a lot of the numerical instructions like add, multiply, and so on. Where it gets a little bit tricky is in all the control flow statements. One of the most notable things about WebAssembly is that it has no unstructured control flows. So you cannot just go to an arbitrary address in the instruction set. You have explicitly structured code constructs like loop and if and blocks. And you can only jump to specific parts like the top of a loop or the top of a block. So when in WebAssembly you say branch, that's more like a continue or a break, which exits the loop or goes back to the top of. And the index of a branch statement is not the index of an instruction to jump to, but how nested it is and to what level of nesting to jump out to. So these control flow constructs are a little bit tricky to encode in Isabelle, but the paper goes over how they modeled that. The next thing you have to formalize is the type system. We need all WebAssembly programs to be well typed in the sense that the types of values on the stack must match what is expected by the instructions. For example, if you run across an add instruction, the expectation is that the top of the stack contains 2 numerical values. Fortunately, because of all these structured control flow instructions, WebAssembly can be type checked in one linear pass. The type checker is fairly straightforward. The notation here is standard type checking notation, which basically lays out the rules for what configurations are well typed. For example, if you look at this rule over here for binary integer operations, this is saying that if the top of your stack has 2 values of type t, and those 2 values are of type int, then after the operation, you will have a stack whose top contains 1 value of that same type t. And while they've done this formalization, they've encoded in abstract ways what's written in the spec. But as they've done that, they followed the principle of what they call eyeball closeness. And this is done whenever you're trying to formalize a spec that's written in a non-formal plain language. And what eyeball closeness means is that you could take each line in the specification and relate it to a line or clause in the formal specification as well. Now, once you have the small step semantics and that reduction relationship, as well as a definition of which WebAssembly programs are well typed, you can then get to proving the central result that we're going for, which is that well-typed WebAssembly programs enjoy progress and preservation. Preservation and progress are two of the most fundamental things you can prove about a well-typed system. The preservation property says that if you have a well-typed configuration and via your small step semantics, you take that configuration to another new configuration, then this new configuration is well typed as well. So this is basically saying that if you start with a well-typed program and keep following your semantics, you will never end up with a program that is not well-typed. The second fundamental property you want to prove is progress. And what the progress property says is that if you have a well-typed configuration, you can always take a step forward to another well-typed configuration. The only exception to this is if you are in a known ill-defined state, which in WebAssembly is modeled as a trap, which is basically an exception. And this is quite an achievement because, as the author says here, this is a fully mechanized proof of these type soundness properties. And this is the first time this was done for WebAssembly. And very notably, and this demonstrates the value of trying to formalize these semantics, while they were doing this, they found a couple of bugs in the spec. One had to do with how the trap instruction is propagated, and the other one had to do with the semantics of the return statement. The original semantics allowed you to return to arbitrary places and not just the outside of a function call. And so both of these semantic bugs, so to speak, were fixed in the specification, and they were exposed as a result of this formalization effort. So that was a quick look at a paper that formalizes the semantics of the WebAssembly instruction set and proves it to be sound in terms of preservation and progress. There's still a lot of work to be done. For example, in formalizing the memory model, in formalizing how WebAssembly interacts with other modules and other functions when it calls out to things that are outside WebAssembly and so on. So I hope you found that useful, and I will see you next time. Thank you very much.